All right, this is where it gets fun. So we've laid down the basics. You had PLQ9 kind of talking to you about how enzymes work. We just spent a little bit of time talking about energy transformations in these reactions, and now let's actually put it into a real life context for you. This is a specific metabolism that most of you have probably experienced, and even if you have not experienced it personally, you at least are aware of it in a social context. So we've so far just talked about single enzymatic reactions, one substrate, one enzyme, and then creating products from that. But often in life and in the body specifically, there is a metabolic process in which a substrate and an enzyme create products, and then those products interact with different enzymes that create different products, and so on and so forth. We'll start here with an example of just a two-step pathway. So we're going to start with one substrate, alcohol or ethanol specifically. We're going to interact with one enzyme, alcohol dehydrogenase, to create a new product, acetaldehyde. And then that acetaldehyde product is going to interact with a different enzyme, aldehyde dehydrogenase, to create a final product, acetate here. And this is basically just how your body digests alcohol, how your body helps to clear alcohol from your system. So in people who have functional enzymes in these pathways, in this metabolism, in people that have alleles that create alcohol dehydrogenase and aldehyde dehydrogenase through gene expression, through transcription and translation, that fold correctly, that are functional, you are going to see ethanol interacting with alcohol dehydrogenase to create acetaldehyde, and then acetaldehyde interacting with aldehyde dehydrogenase to create acetate. The body cannot get rid of ethanol on its own. It cannot get rid of acetaldehyde on its own, but it can pretty easily get rid of acetate in your urine. So over the course of clearing alcohol from the body, you're creating lots and lots and lots of acetate in this two-step process and allowing that to be to leave the system through the kidneys and the urinary tract. And if we want to kind of bring this back around to our previous video, just remember that enzymes are kind of like lock and key. So this alcohol dehydrogenase lock is only going to fit the alcohol key in this scenario. Acetaldehyde does not fit into alcohol dehydrogenase's lock. Acetaldehyde only fits into aldehyde dehydrogenase's lock. And same thing here. Aldehyde dehydrogenase, this lock does not fit an alcohol key. It only fits an acetaldehyde key. And so each enzyme has a specific active site that will only fit with very specific substrates. So we need two enzymes to get to acetate from alcohol, and we have to go in a two-step process to get all the way there. And again, you can kind of think about this as, or remember that this is intermolecular interactions facilitating this process. And so if this substrate is alcohol dehydrogenase, alcohol here, the ethanol, is sitting into the if this enzyme is alcohol dehydrogenase, the substrate is ethanol. The ethanol is sitting into the alcohol dehydrogenase active site and forming a intermolecular interaction there via van der Waals or via hydrogen bonding or ionic bonding here, allowing for that initial transformation to acetaldehyde. And then acetaldehyde does the same thing with aldehyde dehydrogenase to create acetate. Okay. So this is how it should work. Alcohol to acetaldehyde to acetate cleared from the body. This is how it does work in the majority of people. And you can imagine that different people, depending on how much alcohol they consume, are creating different amounts of these two enzymes. Remember that gene expression can be altered by environmental influence. And so if you have a high intake of alcohol, your body might make more alcohol dehydrogenase and more aldehyde dehydrogenase than somebody that does not consume a lot of alcohol. Or in other scenarios, you might have a dysfunctional allele for one or both of these enzymes. And you might have, because we're diploid, remember we have two alleles for every gene, maybe you have, maybe you're homozygous recessive for aldehyde dehydrogenase. Maybe you make two bad copies of that enzyme and you cannot create an enzyme that is able to break down acetaldehyde and create acetate. Or maybe you're heterozygous. Maybe you make one bad enzyme and one good enzyme, so this part of the process is a little bit slower than in somebody who makes two good copies. But any sort of change in the enzymes here, any sort of change in the creation of these via gene expression can change how fast this process is able to occur. Or in other words, it can change how well your body is able to tolerate alcohol. All right, so I want you to kind of consider a scenario here. Consider this. When they consume alcohol, individual A digests acetaldehyde at the average rate. Right here, acetaldehyde. So this first person, individual A, is able to break down acetaldehyde and produce acetate normally. But individual B does not digest acetaldehyde at all. So individual A is able to do this reaction. Individual B is not able to do this second part of the reaction. If you were investigating the activity of aldehyde dehydrogenase in these two people, what pattern might you observe in this experiment? So if you're looking at the activity of aldehyde dehydrogenase, what do you expect the differences to be between acetaldehyde to acetate in individual A and acetaldehyde to acetate in individual B as it's processed through aldehyde dehydrogenase? I'll give you just a couple of seconds to think about that, maybe jot down in your notebooks what you think the difference is, and I'm going to get set up here to do the big reveal in just a second. Okay. So this is actually a real reaction in people. People that are not able to do this second part of the reaction, people that do not have functional aldehyde dehydrogenase, have what we call alcohol flush syndrome. And alcohol flush syndrome you might be familiar with. If you are somebody that consumes alcohol and then afterwards you feel like really hot, or your skin gets very red, or you get a headache pretty much immediately, you might be suffering from this condition. And it's usually something that is noticeable to other people. So if we look at this woman here who does not create functional copies of aldehyde dehydrogenase because her alleles are dysfunctional, she, before consuming alcohol, has no flush reaction, and after consuming alcohol has this sort of red complexion. And that is because our bodies treat acetaldehyde as a toxin. Our bodies cannot deal with a buildup of acetaldehyde in our systems. And so this woman her body is responding to this toxic acetaldehyde building up and not being able to break it down. And this is not a very comfortable scenario. She would really feel quite unwell if she drank too much because the body is reacting to trying to clear this toxin. So if we want to bring it back to this scenario here, and I'm asking about the activity of aldehyde dehydrogenase, in individual A, aldehyde dehydrogenase works just fine. In individual A, aldehyde dehydrogenase over and over and over again is breaking down acetaldehyde into acetate. But in individual B, aldehyde dehydrogenase is the wrong shape. And because it's the wrong shape, the active site doesn't fit around acetaldehyde. Because it's the wrong shape, the lock doesn't fit this key. And so you're never able to create acetate. And if we want to put this into a visual perspective, we can think about this as reaction rate on the y-axis and substrate concentration on the x-axis. So in somebody who has functional aldehyde dehydrogenase, as you add more and more and more substrate, as you add more and more and more acetaldehyde, as the body breaks down more and more and more ethanol, all of that acetaldehyde is interacting with functional aldehyde dehydrogenase. And so you've got the reaction rate increasing and increasing and increasing and increasing. The production of acetate increasing and increasing and increasing over time. So you're sort of building up more and more and more product as you add more and more and more substrate, which makes sense. But if we want to think about like why it's slowing over time, you can imagine every single enzyme, even though it can be reused over and over again. And let me grab my pen again. I like to draw my enzymes as little Pac-Men. So let's say this is somebody who makes functional aldehyde dehydrogenase. And they've got lots of it. So there's lots and lots and lots of functional aldehyde dehydrogenase in this person's body. Specifically, it's made in the kidneys. But now let's go ahead and add a lot of acetaldehyde. All right, so as this person consumes alcohol, this is individual A here. As individual A consumes alcohol, the first reaction breaks down that ethanol and produces acetaldehyde, these little red circles here. And through diffusion, through random interaction, some of this acetaldehyde is going to find its way into the active site of aldehyde dehydrogenase and sit in that little active site there and start the breakdown process. And so you're going to see through time, as you add more and more and more substrate, you're going to get this reaction going up because more active sites are occupied. Let's add more. If we add more, maybe another active site is occupied. As active sites get occupied, we move up and up and up along this curve. But eventually, we add more and more. This person's drinking more and more and more ethanol, more and more and more alcohol. And eventually, all of these active sites get occupied. And once all the active sites get occupied, you can add infinity more substrate. You can add tons of acetaldehyde to the system, lots and lots and lots more. But once all the active sites are occupied, you're going to kind of level off here at a set reaction rate. If there's no more active sites available, then you can't have the reaction go any faster. As soon as this acetaldehyde is broken down into acetate, it'll move out of the active site and the next one can come in, but you're going to kind of see this plateau taking place in any individual as active sites get occupied. And so here we've got individual A. Okay. And then lastly, before we move on to the next kind of idea here, if we wanted to add individual B to this graph, so remember individual A was processing these things normally. If we wanted to add individual B to this graph, how do you think their reaction rate curve would look over time? I'll give you a minute. Okay, remember that individual B was not able to process acetaldehyde at all. Individual B's aldehyde dehydrogenase was not functional. So if you've got a ton of enzyme in the body that is not functional, you're never going to get any sort of reaction. So individual B would kind of flatline down here. You can add lots and lots and lots of substrate. You can keep increasing ethanol in the body. You can keep increasing aldehyde dehydrogenase, keep increasing acetaldehyde in the body, but you're never going to increase reaction rate because in individual B, their enzymes are a different shape. So let's say their Pac-Man looks more like a donut. And so maybe in individual B, you've got this scenario where they have lots of enzyme here, but it's never the right shape to allow acetaldehyde to sit inside the active site. And so as this person consumes more and more and more alcohol, the first step in the reaction takes place. They produce lots of acetaldehyde, but that acetaldehyde never gets broken down. That acetaldehyde never gets converted into acetate via this enzymatic reaction. So they've just got this buildup of acetaldehyde in their systems, and the enzyme is not involved in the reaction at all. So in this person, we're putting more and more and more substrate into the system, but we're never increasing reaction rate. And so you can think about this as, and I'll add a label here. Here's individual B, just kind of flatlining down here. We can think about individual A as being homozygous dominant, making lots of copies of the correct enzyme because they've got 2 copies of the good gene for that enzyme. You can think about individual B being homozygous recessive. They've got 2 copies of the bad gene, and so they don't make a functional enzyme here. What do you think would happen if we had a heterozygote? What do you think would happen if we had somebody that one of their alleles codes for this enzyme, the other allele codes for this one? How would their curve look on this graph? And you're probably kind of thinking that it would be somewhere in the middle. This person isn't going to be able to process alcohol quite as well as individual A, but they'll definitely be able to process it better than individual B. Some of their enzymes in their bloodstream will look like this, not able to help move acetaldehyde out of the system, but some of the enzymes in their bloodstream will look like this, able to help break that down and produce acetate. So somebody who is a heterozygote for this gene is going to maybe have a little bit of an alcohol flush reaction, but still be able to clear alcohol from the body much better than individual B would, much better than somebody who has a full alcohol flush reaction here. Interestingly, if you want to think about how we treat in recovery for alcoholics, we can add some medication that inhibits the functionality of aldehyde dehydrogenase, and so it kind of mimics individual B here. It creates a condition where the body builds up acetaldehyde and people have this kind of negative toxic reaction, and so it kind of helps to allow people to start to build this relationship between drinking alcohol and not feeling well, which sort of puts them off drinking more. And interestingly enough, if you look at the rates of alcoholism in the general population, people who are homozygous recessive for this gene, people who only make bad copies of this enzyme and are not able to clear acetaldehyde from the body tend to have a much lower rate of alcoholism, just because the experience of drinking alcohol is so unpleasant for them that they don't drink it as much as people who are able to process it. People like individual A who are able to move it out of the system. Okay, we'll go ahead and stop that there, and then we will move on to the next application in the next video.